Okay, so when we left off in the last video, we were looking at example 9.4, which asks us to draw a Lewis structure for nitric acid. And it gives us some really nice hints about the structure in that the 3 oxygen atoms are going to be bonded to the nitrogen atom. And the hydrogen is going to be bonded to one of those oxygens. Okay, so just by reading the problem, you could start by doing this. You could say, okay, I have a nitrogen. It's got 1, 2, 3 oxygens bonded to it, and it says that the hydrogen atom is bonded to one of the oxygens. So you could pick any one of the 3, doesn't matter. I'll pick this one here, and we'll draw a bond like that. Okay, so you could start there. Now, what I told you in the last video is that I like to start by tallying up the total number of valence electrons. That's usually what I do, but let's do a second step this time. So hydrogen has 1 valence electron. It's in group 1A. Nitrogen has 5 valence electrons. It's in group 5A. Oxygen is in group 6A. It's got 6 valence electrons, but I have a total of 3 oxygens. So that's 6 times 3. So that's 18 plus 5 plus 1. So that's 18 plus 6, which gives us a total of 24 electrons. If I look at what I've drawn down here, how many electrons have I used up so far? The answer is 1, 2, 3, 4, 5, 6, 7, 8. 24 minus 8 is 16, so I have 16 electrons left to go. You can see that the hydrogen is perfectly satisfied, isn't it? Hydrogen only ever needs to have 2 valence electrons near it to be isoelectronic with helium, and those 2 electrons are found in that bond. Whereas all 3 oxygens and the nitrogen, not one of them has an octet. Well, if we've used up a total of 8 electrons and we have 16 to go, let's just start putting them around. If I put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Let's say if I try something like that. Well, you look at this oxygen. What's it surrounded by? 1, 2, 3, 4, 5, 6, 7, 8 electrons. Hey, it's got an octet. It's good. What about this oxygen? It's surrounded by 1, 2, 3, 4, 5, 6, 7, 8 electrons. It's also good. What about this oxygen? It's surrounded by 1, 2, 3, 4, 5, 6, 7, 8. It's also good. So now I've got 3 oxygens, and they're all good. And I already decided that my hydrogen was good. What about my nitrogen? Does it have a complete octet? The answer is no. It's surrounded by 1, 2, 3, 4, 5, 6 electrons. What am I going to have to do? I'm going to have to take one of the lone pairs and make a new bond. I'm going to take this pair of electrons right here, erase them, and I'm going to use them to make a new bond to my nitrogen. Now the oxygen that was changed is surrounded by 1, 2, 3, 4, 5, 6, 7, 8. But now you also see that the nitrogen is surrounded by what? 1, 2, 3, 4, 5, 6, 7, 8. So all 3 of the oxygens and the nitrogen all have complete octets, and the hydrogen has a complete duet. This is a perfectly acceptable Lewis structure. Now, if you had, say, put the double bond down here, that is also perfectly fine. What if you had done something different? What if you had taken we'll just leave it like that for now. Let's try another example. I've got one for you off the top of my head. Let's try this. This is called formic acid. Okay. Before you start to try formic acid, I want to give you some quick and dirty rules. Nitrogen that you saw on the previous example in nitric acid usually has 3 bonds, usually, not always, has 3 bonds and 1 lone pair. Okay? Carbon usually has 4 bonds and 0 lone pairs. And oxygen usually has 2 bonds and 2 lone pairs. Okay? And hydrogen only ever forms 1 bond and nothing else. If you can memorize these few rules right here, also other like little things like I taught you that fluorine always has 1 bond and 3 lone pairs, like that. If you can memorize this little group of rules, it can really help you get through problems like this formic acid one pretty quickly. How many total valence electrons are there in formic acid? I have 1 from my hydrogen, 4 from my carbon. I've got 2 oxygens. They both have 6, and I've got 1 from this hydrogen. I tally all those up, and I get a total of 18 electrons. Now, the reason why the formula is instead of H2, instead of C2, H2, CH2O2, the reason that it's not written like that, there's nothing wrong with that, but the way that it's written here, it tries to give you some information as to how the atoms are connected to each other. So what it's telling you is that you have a hydrogen connected to a carbon, which is connected to an oxygen, which is connected to a hydrogen. And we're going to put the other oxygen like this. Now I've used up a total of 1, 2, 3, 4, 5, 6, 7, 8 electrons. I've got 10 left to go. Well, if oxygen always forms 2 bonds and 2 lone pairs, and carbon always forms 4 bonds, carbon already has 3 bonds, doesn't it? So to this oxygen, I'm going to put a bond and 2 lone pairs. And to this oxygen, I'm going to put 2 lone pairs like that. Now you can see that the carbon and both oxygens have complete octets, don't they? The 2 hydrogens have a complete duet, and this is a perfect Lewis structure. Let's try another one. It says here, write the Lewis structure for the carbonate ion. We spent a lot of time looking at polyatomic ions this semester, so you should know that carbonate is CO3 2-. How many total valence electrons are there in carbonate? Well, I've got 4 from carbon. Each oxygen has 6, and there's 3 of those. Then I'm going to add 2 because I've got 2 extra electrons for the 2- charge. When I tally all that up, I've got 18 plus 6. Sorry. Did I do that right? I've got 18 plus 4 is 22, 24. Sorry. I've got a total of 24 electrons. I'm going to give you a second, and I'm going to set a timer for this to see if you can give it a good stab here and see if you can get something started. Hey, Siri, set a timer for 60 seconds.
Okay, your timer is set for 1 minute.
All right, there goes our timer. All right. Well, we know that most of the time we put the least electronegative element, which would be carbon in this case, in the center. It's connected to the 3 oxygen atoms like this. Now I've used up a total of 1, 2, 3, 4, 5, 6 valence electrons, and I've got 24. That means I've got 18 to go. Well, remember that carbon usually forms 4 bonds, so I'm going to put another bond to my carbon like this. What else did I tell you? I told you that oxygen usually has 2 bonds and 2 lone pairs, just like you saw in H2O. 2 bonds and 2 lone pairs. But sometimes, as in the nitric acid that we saw, oxygen will have 1 bond and 3 lone pairs. Now, I've used up a total of 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. I've got 16 left to go. Let's start filling up the octets of the oxygens. Now, this oxygen has an octet. 1, 2, 3, 4, 5, 6, 7, 8. And these oxygens have 1, 2, 3, 4, 5, 6, 7, 8. So everybody's got an octet. And I've accounted for all 24 electrons. The question then becomes, what about the 2 minus charge? There's a couple of ways you can address this. When I teach Chemistry 101, which is a lower level than the class that you're in, which is Chemistry 111, what I teach my students in that class is that we put square brackets around our Lewis structure, and then we put the charge on it like that. But in Chemistry 111, we go one more step, and we write the negative charges next to the atoms that have negative charges. And to do that, we calculate the formal charge of each atom. Let me show you how to do it. Formal charge of each atom in this structure is equal to the number of valence electrons for that atom, subtract the number of sticks, which is the bonds, minus dots, which is the number of unpaired electrons. So if I want to calculate the formal charge for this carbon, carbon has 4 valence electrons. It's surrounded by 1, 2, 3, 4 sticks. And it's got no lone pairs on it. 4 minus 4 is 0. What about this oxygen? Oxygen has 6 valence electrons. This oxygen is surrounded by 2 sticks, or 2 bonds, and 1, 2, 3, 4 electrons. 6 minus 2 minus 4 is 0. So there's no charge on that oxygen either. What about this oxygen? It's got 6 valence electrons. It's got 1 stick. And it's got 1, 2, 3, 4, 5, 6 electrons. 6 minus 1 minus 6 is -1. That means that this oxygen has a negative charge. The same thing applies to this oxygen. It's got 6 valence electrons minus 1 stick or 1 bond and 6 electrons, -1. -1 plus -1 gives you -2. And there we go. Give me a thumbs up if you follow me on the concept of formal charge. All right. Now, if you look at the textbook's definition of formal charge, I think it's a little more complicated. It says here, formal charge is formal charge on an atom, is total number of valence electrons, good, minus the number of non-bonding electrons, so that's the electrons that are just dots, minus half the number of bonding electrons. So since there's 2 electrons in a bond, you cut it in half, okay? So it's kind of, since there's two electrons multiplied by half is 1. It's kind of easier to do it my way, I think. All right. It's important that you know that the sum of the formal charges of the atoms in a molecular ion must equal the charge on that molecular ion. If you try to come up with a structure for formaldehyde, and if you've taken biology, I'm sure you've heard of formaldehyde. It's used as a preservative for tissues. Here's a Lewis structure that was proposed for formaldehyde. Okay? Technically, when you look at this Lewis structure, it doesn't look all that bad because every element has an octet or a duet. The two hydrogens both have a duet. The carbon has an octet, and this oxygen has an octet. But when you calculate the formal the carbon and the oxygen, you see the carbon has a formal charge of -1, right? Where did that come from? Carbon has 4 valence electrons. Subtract 1, 2, 3 sticks. Subtract 2 dots. That gives you -1. The oxygen, using the same formula, has a charge of -1. And so what we want to do in our Lewis structures is we want to minimize the number of formal charges. And when we seek to minimize the number of formal charges, we find there's actually a better Lewis structure for formaldehyde. It's shown right here, where the carbon has 2 single bonds and a double bond, and the oxygen has 1 double bond and 2 lone pairs. And now you can see the formal charge of the oxygen and the carbon are both 0. And so this would be the correct Lewis structure for formaldehyde. It asks us now to write the formal charges of the carbonate ion. We've already done that a few seconds ago. So I want to back up to our nitric acid molecule. Nitric acid doesn't have an overall charge, does it? It's a neutral molecule. But there are formal charges in this Lewis structure. I want you to find the formal charges in this Lewis structure. I'll give you 60 seconds. Hey Siri, set a timer for 50 seconds.
Okay, your timer is set for 50 seconds.
All right, can anybody tell me where I might find a formal charge in this molecule? Okay, great. Some people are saying there's a +1 charge on the nitrogen. I think those people are 100% correct. Nitrogen has a total of 5 valence electrons. It's surrounded by 4 sticks and 0 dots. That gives me a charge of +1. I can write that like this. There's a positive charge on my nitrogen. And then Bruce says the oxygen on the left has a formal charge of -1. He's also correct. right? This oxygen has 6 valence electrons. Subtract 1 stick, 6 dots gives you -1. So I put a negative charge here. +1 and -1 equals 0. And so even though there are formal charges in nitric acid, overall, the charge is 0. So again, our Lewis structure is great, and we've assigned the formal charges to the atoms in the molecule. Here are some more rules concerning formal charges. If you have a neutral molecule, like nitric acid that we just looked at, the Lewis structure in which there are no formal charges is preferable to one in which there are formal charges present. The Lewis structure with large formal charges are going to be less plausible than those with small formal charges. And finally, comparing Lewis structures having similar distribution of formal charges, the most plausible structure is one in which the negative formal charge is on the more electronegative atom. We got 7 minutes left. Let's try some more examples. What if I wanted to draw a Lewis structure for nitrogen dioxide, NO2? How would I do that? First thing I'm going to do is tally up the total number of valence electrons. I've got 5 for nitrogen. There's 6 for oxygen, but there's 2 oxygens. I meant NO2 minus, the nitrite ion. Like, that's not right. I didn't want to get into unpaired electrons yet. So I'd add 1 for the negative charge. So that's 12 plus 6. That gives me a total of 18 valence electrons. I'm going to start by putting my least electronegative element in the middle. Put my oxygens on the end like that. Now I've used up 4 electrons. I've got 14 to go. If I fill up the octets of the oxygens like this, now I've used up a total of 16 electrons. I can't have more than 8 electrons around my oxygen, so I'll put 2 electrons here. Well, you can see there's a few problems with my Lewis structure. First of all, I have a -1 charge here, and I have a -1 charge here. I'm doing the formal charges a little bit quicker now. Both of the oxygens have complete octets, but the nitrogen doesn't have a complete octet, does it? What if I take one of the lone pairs from the oxygen, or one of the oxygens, and I make a bond like this? Well, now, if I look at my oxygen on the left, it's got a formal charge of 0, and it has a complete octet, 1, 2, 3, 4, 5, 6, 7, 8. What about my nitrogen? It's surrounded by 1, 2, 3, 4, 5, 6, 7, 8. It's got a formal charge of 0. Let me prove it to you. Nitrogen has 5 valence electrons. Subtract 3 sticks and 2 dots. Well, that leaves the oxygen on the end. If you've been paying close attention, you might remember that when oxygen has 1 bond and 3 lone pairs, it's got a negative charge. And so I have a charge of -1. Is this a good Lewis structure? Absolutely. All of the atoms have a complete octet. I have my formal charge of -1, and that formal charge is placed on the most electronegative element. Remember that electronegativity increases going across a period. So as we go from carbon to nitrogen to oxygen to fluorine, fluorine is 4.0, oxygen is 3.5, nitrogen is 3.0, and carbon is 2.5. Fluorine gets the gold medal. It's the most electronegative element in the periodic table, but oxygen takes the silver medal. It's the second most electronegative element in the periodic table. So we have a perfectly reasonable Lewis structure for the nitrite ion. Let's try one more. Let's try cyanide. Cyanide is Cn minus. let's tally up the number of electrons. Carbon has 4, nitrogen has 5, and then I have 1 for my -1 charge. That gives me a total of 10 valence electrons. There's only one possibility, right? And that's to connect my carbon and my nitrogen like this, which uses up 2 electrons. That means I have 8 left over. 1, 2, 3, 4, 5, 6, 7, 8. There's a big problem here, isn't there? Neither one of these atoms has a complete octet. If I take this pair of electrons and I make a bond like this, now you can see that my nitrogen has an octet, doesn't it? 1, 2, 3, 4, 5, 6, 7, 8. However, my carbon does not have an octet. 1, 2, 3, 4, 5, 6. Well, if I was to take the pair of electrons from the carbon and put it here like this, there's a big problem. Now my carbon still doesn't have an octet, and my nitrogen is surrounded by 10 electrons. So that's no good. What if I took one of the lone pairs from the nitrogen and I connected it like this? Now my nitrogen has an octet and my carbon has an octet. Now, since electrons repel each other, I'm going to draw those electrons as far apart from each other as possible. If I calculate the formal charge of my nitrogen, it's 5 valence electrons minus 3 sticks and 2 dots. That's 0. If I calculate the formal charge of my carbon, it's 4 minus 3 sticks and 2 dots, which equals -1. And so I will put the negative charge on my carbon like this. Now, you might be wondering, hey, Mr. Dion, your negative charge is on the less electronegative element in this Lewis structure, which is perfectly fine. But what you'd see is if you try to manipulate this so that you have the negative charge on the nitrogen, your carbon will become electron deficient, meaning it will not have a complete octet. Before our lecture next Tuesday, what I highly recommend is that you read through the rest of Chapter 9 and that you spend a lot of time doing practice problems. If you go under the content folder on our D2L page, you'll see that I have suggested problems and I've also provided the solutions to those problems. I can't stress it enough that the best way to master Lewis structures is to practice them as much as possible.